Good afternoon. My name is Hunter Manning, and this is my submission for Lab 5 of Physics 1. In this lab, I will be focusing on the motion of a falling slinky. In this video, I will first introduce the lab while identifying the system and its surroundings. I will then dive into some key concepts behind this experiment. Then, I will analyze the motion of the object through the tracker software. Next, I will discuss the computational model used to predict the object's motion through GlowScript. Then, I will discuss the results of this experiment. And finally, I will answer the discussion questions I created. The purpose of this lab is to observe the effects of gravitational and drag force on the motion of a slinky. Using the experimental data collected, a computational model will be made that accurately predicts its motion. The objective of this lab is to apply Newton's second law to real-world scenarios. In this lab, the system is the slinky itself, and the surrounding is the Earth. I will now discuss some key concepts in this lab. This lab is highly reliant on Newton's second law. Based on this law, we can identify two main equations. The first being that the force is equal to the mass times its acceleration, and the second being that the net force is equal to the change in momentum divided by the change in time. Further, the position update formula was used in this lab. This formula says that the final position is equal to the initial position plus the average velocity times the change in time. We also use the velocity update formula, which states that the final velocity is equal to the initial velocity plus acceleration times delta t. Finally, we use the drag force. This equation tells us that the negative of the magnitude squared times v hat is equal to the drag force. I will now discuss the tracker model, aka the observational model. The initial conditions of this scenario had an initial velocity set to 0.00 meters per second. The initial position was found to be minus 8.3 times 10 to the negative 3 in the x direction, 1.25 times 10 to the negative 2 in the y direction, and 0 meters in the z direction. The mass of the slinky was found to be 0.25 kilograms. In setting this up, the origin was set to the bottom of the slinky, and 1.77 was used to calibrate this model, as 1.77 was the average height of a male. I will now discuss my GlowScript analysis. The structure of this code was largely the same as found in Lab 2, so I began by copying and pasting that original GlowScript code into this lab. In this, I edited the mass of the slinky to be 0.25 kilograms. I set the slinky's original position and original velocity to be the same as in the initial conditions as the observational model. I set the value of g, the magnitude of acceleration due to gravity, to be 9.8. I also set b, the drag constant, to be 2.68, corresponding to my calculations. The net force acting on the slinky is equal to Ft plus the weight of the slinky. Ft is equal to the mass of the slinky times j hat. Weight is equal to the mass of the slinky times the force of gravity. Next, I inputted the velocity update formula as shown on line 77. This formula says that the final velocity is equal to the initial velocity of the spring plus the net force divided by the mass of the ball, which is the acceleration, times delta t. I also inputted the position update formula on line 79 to map the position of the ball over time. This formula states that the final position of the ball is equal to the original position of the ball plus the ball's velocity times delta t. Both of these formulas are heavily reliant on Newton's second law. I further split up this code to correspond to the times when the ball started moving vertically. Based on my tracker analysis, I saw that the ball stayed in relatively the same position below 1.7 seconds. After it started moving, I saw that it began moving after 1.7 seconds and hit the ground at 2.9 seconds. So I inputted this as such. Comparison of results. As you can see below, both of the models indicate a downward sloping curve after a period of no vertical movement, indicated by the horizontal line at the beginning. This is a result of the net forces on the slinky in the y direction. The computational model and observational model are somewhat similar, but not exactly the same. Some sources of error that could contribute to this are the early start and late stop time of my own tracking of the motion of the slinky. I will now respond to my own created "what does it mean" question. What does it mean when different parts of the same slinky begin to move at different times? Each section of the slinky responds to forces differently. At release, the top part is under freefall, while the lower portion is experiencing tension, holding it in place. This discrepancy highlights delayed force transmission, where parts of the slinky at the top may be moving while the bottom may be held stationary, as we saw in the video that was linked on Canvas. Thank you.